Good evening, everybody.
Ma'am, in this, you are solving the problem, or solving the activity questions, or you go through with concept and then you solve?
A little bit about the concepts, and after that, we will solve some problems as well. Okay?
Okay, sir.
This is regarding week 8.
No, it
No,
is regarding
week
week
7.
7. Week 7.
Okay, okay.
It is regarding week 7. Okay, the remaining concepts, actually, some of the concept left. So that. So, so in this one, we have already covered the similarity and equivalence of matrices. Equivalence and similarities. Equivalency and similarity. Okay, so now is affine subspaces. Okay, affine subspaces and affine mapping we are going to cover in this session, and dot product and other things as well. Okay, so what are affine subspaces? So before this, you are aware of the subspaces. What are actually subspaces? These are just a part of space. Just a minute. Okay. So these are just subspaces or a part of vector spaces, uh, or a subset of vector spaces that follows the multiplicative closure and additive closure properties. So suppose this is my R2 vector space. So any line in this one that passes through the origin, okay, so it will be my subspace. Okay, or the whole plane will be my subspace, or any or the origin is will be my subspace if I take this point. Okay, so what are affine subspaces? Basically, they are just translating the points of the subspaces. When we translate a point, so it will become, or translate a whole space, then it will become an affine subspace. Affine subspace. Okay, so means if I have a line that is passing through the origin, and if I translate its each point or each vector by some distance, suppose I translate it here, this point translated here, this point translated here. Okay, so now the new line will pass, will go through here. So this is my affine subspace. Okay. So this distance or this vector, that is actually translating. So we sometimes call it translatory vectors. Okay. So this defines that how much and in which direction our points are going to be translated. So here you can see this point V is going to belong to the vector space, the whole vector space R2 we are considering, and this is our subspace. This was okay, and this was our affine subspace. So this U is representing this subspace, okay, and this L is representing this affine subspace, affine subspace. Okay. So simply you are aware that this is our subspace, all the points in this form x comma 0. Okay. So this is nothing but this line. So it is saying that if I translate this each and every point of this by 0 comma 1, so it gets shifted from here to here, it will get shifted. Okay, so now it is affine subspace. Okay, if I want to shift my subspace from this x-axis to this line, so it is not always that I choose this 0 comma 1. Maybe I can choose this 2 comma 1. Okay, means this point gets two units gets right side and one unit gets upside. So this point translated from here to here. Okay, next point that was here will get translated here. Okay, this point here will get translated here. So like this we can continue, still we are getting the same affine subspace. Okay, but now whenever I look at it, look at any specific vector, then it is translated in some other direction. Okay, earlier every point was translated in this direction, now it is in this direction. Okay, but we are getting the same affine subspace. So next thing, dimension. How do we calculate the dimension of any affine subspace? So basically, dimension of affine subspace is defined as the dimension of the corresponding subspace. Firstly, we will find out the subspace corresponding to that affine subspace, and then we will calculate its dimension. Then we will get the dimension of the affine subspace. Okay. such that if you are using this zero subspace and you translate it has only one vector, that is 0 comma 0, okay, or 1 point. And if you translate it to some a comma b, so now new coordinates will be a comma b, where a or b belongs to any, they are actually some real number. So this is our affine subspace, okay. So it will also have zero dimension. Next is this one, any straight line if you are considering. So if it is your straight line, okay, with some slope m, okay. So if I find any affine subspace, so it will be of dimension 1 as well. Same for the other things. For complete two-dimensional space vector space you are taking, or a two-dimensional subspace you are taking, so its affine subspace will have the dimension 2. Same thing applies for the three-dimensional space, okay. After there is the addition and the multiplication laws. So how do we add the two vectors that are belonging to some affine subspace? How do we add them? So we firstly find out this translatory vector, and we take that vector that is inside this, and then we add them. How do we add them? Suppose L is some point like this. So I am taking this example same, that is v plus u. V is our translatory point or translatory vector, that is translating, means from in which direction each point should be translated. And this u is going to belong to our subspace, okay. Next, this was my point L1. This vector is my L2, and I want to add. So the same translatory point we are going to use, and I am going to add, suppose, u dash. So what will be their addition? It states that this translatory, we are not going to add this translatory point. We are just going to add this subspaces part. Okay. So their addition will be u plus u dash, and only once we are going to give this translatory vector.
Can you show some examples, sir?
Yeah. Suppose your translatory vectors, sorry, your affine subspace look like this, x comma 1. Okay. So from here you can get that it is considering all x comma zeros, and you are having 0 comma 1 as your translatory vector, okay. So if you want to add 2 comma 1 and 5 comma 1, okay, so how can you add? You will get 7 comma 1, means you can write 2 comma 1 as 0 comma 1 plus 2 comma 0, right? And then you can write this 5 comma 1 as 0 comma 1 plus 5 comma 0. So if you add, so you add this subspace part, okay, then you added 7 comma 0, and then added this translatory vector to it. So you got 7 comma 1.
So this
Like this.
translatory vector on addition will remain the same.
The addition on this translatory vector is not going to work. You don't have to add these 2 points. You just have to add it once after that.
Okay.
Okay, what the thing is this? We are going to use this thing that we are following here. It is actually related to the subspace. You are aware of that. How do we add in subspaces? So it is we are using the standard addition and multiplication laws. So if I have a vector 2 comma 1, so I know that its part, which is this translatory point, is common for this whole space. Okay, it is same. Whole affine subspace, it is same, okay. So I am removing it. So whatever I left is 2 comma 0, and from 5 comma 1 whatever left was 5 comma 0, these two parts, okay. So you know how to add in subspaces. Just add the first component with first and second with second. So you got this, okay. But you now have to convert it to the affine subspace. You need this point to be in that space where you are taking the points. You took this point from, and you took this point from. So now you have to again add this 0 comma 1 to get the answer, like this. Same apply for the multiplication. Is that clear?
Here u and u dash belong to same subspace.
Yeah, yeah. Both are from same subspace. Same subspace. This V also belongs to this same subspace, okay?
So in in basically for this component V, the normal addition and multiplication, it doesn't apply, right?
No, no, no. It is not going to apply here. Yeah.
Okay.
Basically, what we are doing, we are converting the affine subspace to a simple subspace, and then doing the addition multiplication things here, and then again converting it to affine. This is basically the pathway. So same here. you can see that when we are doing multiplication, suppose I want to multiply this x comma 1 vector with some constant c. So what I will
Okay,
do, I will
Ex
multiply
comma
this.
one.
Yeah, cx comma 1 I will do it
Okay, okay,
in this.
okay. Okay, that vector that definition thing. Okay.
Yeah. What are we, what I can write this? This is nothing but 0 comma 1 I took out and x comma 0. So this now this multiplication will work on only on this part. C times x comma 0,
Okay,
and
okay.
then we added this part.
Okay, so basically 0 comma 1 is a translation, right?
Yeah, just translation. So we firstly remove this translation to get our subspace or the point, the image actually, image of that point in the subspace. And the image that I got, I will use it for the multiplication and addition. And then again, I convert it into my affine subspace. Okay. Any query?
Yes, sir. Sir, query regarding scalar multiplication. So, first of all, similar like a fine subspace is given,
Yeah.
then we have to convert it into subspace, right?
Yeah.
For subspace, what we need to do?
Sorry, I'm not getting. For
Uh,
subspace, what you need to do, you need to just remove the translatory point. Means if you are aware that translatory point is 0 comma 1, so subtract it from that, from
this
each
is a
vector.
Mhm.
Yeah, from each vector that is inside your affine subspace, you will remove this part.
For any subspace that is a fine subspace, we have to remove 0 comma 1 to become a.
Not for every affine subspace. Each affine subspace has its respective translatory point or translatory vector. It can be anything. Suppose 2 comma 1 it could be.
It
Okay.
could be what, how we know what is the point
It's
is.
given in the question that this is your translatory vector like this. Okay, just like here, you can see that it is given x comma 1. So you know that every subspace passes through the origin. So if you put the variables value 0, x value, if you put 0, so what you got? 0 comma 1. Okay, so it is passing through 0 comma 1. So means the origin shifted to from here, it is shifted to here. So this is your translatory vector. So you can remove this. That's the part.
After
Suppose,
after removing, then we can add like simpler vector
yeah,
addition.
yeah, simple like simple subspace additions and whatever the laws you follow, you can follow them. Okay.
And for multiplication,
For multiplication, it is okay. For multiplication, you can multiply by 0. Suppose you are multiplying any x comma 1 with 0. So what you will get? 0 comma 1. So this should be your 0 vector. So instead of 0 vector, what you got, you can remove this. So you got 0 comma 1. So this is your translatory point again. Okay. Similarly, you can remove this and then you can perform the multiplication, scalar multiplication in that thing, and then you can come back. Okay.
Excuse me, sir. Could you please take any example with for both the scalar multiplication and the addition? Other
Okay.
example.
Okay. I gave here like this, that if I have a fine subspace like this x comma 1, so that is 2 comma 1. If I want to add 5 comma 1 to this, so what I will do from this 2 comma 1, I will remove this 0 comma 1, and then I got 2 comma 0 and 5 comma 1. I removed this 0 comma 1. I got 5 comma 0. I added these 2 points. Now this one is inside my subspace. Okay. So I need to convert it into the affine subspace. So I will again add this part that I removed. So I got 7 comma 1. Same for multiplication. If I want to multiply, suppose my vector 5 comma 1 with some 7. So what I will do, I will firstly remove this part that was 0 comma 1. So from this vector, if I remove 0 comma 1, so I will get 5 comma 0. Now I will multiply it by 7. So I will get here 35 comma 0. Okay. Now I again add whatever I removed. So I will add it here. So I will get 35 comma 1 like this. Is that okay, Shweta?
Yeah, yes, sir. Thank you.
Next is this. Here we are given some affine subspaces. So we need to find out, no, what we need to do? Yeah, we need to find out their respective subspaces. So first is this one. You can check here that I told already that 0 comma 0 comma 0 should belong to that part. Okay, but if it is not belonging, so we will try some other changes. Suppose I put x value 0, y value 0. So what will I get here? Minus z is equal to 5. So z is equal to minus 5. Means it should go through 0 comma 0 comma 0, but it is passing through 0 comma 0 comma minus 5. Okay, so my point is shifted up to this part. So I can say simply that from x plus 2y minus 5 is equal to 0, sorry, minus z is equal to 0. Okay, this was my part. And if I add in these all these point or all the solution of this space, if I add 0 comma 0 comma minus 5, then this will again form the same affine subspace. In clear? If it is not clear, let me. So here, what was this? I need to I want to find out that it should pass through the origin. So I will write down most of the variables value. I will try to write down as, or I can, what I can do, I can define any two variables in form of one. So suppose I defined z is equal to nothing but x plus 2y minus 5. Okay, this is my z. So I can put this z value here. So I got all my vectors in this form x comma y comma x plus 2y minus 5. Okay. So if I put x and y value 0, so it should pass through the 0. Oh, sorry, origin. It should pass through the 0 vector. Okay. So if I write down x value 0, y value 0, so I got here minus 5. Instead of passing through origin, it is passing through this point. So this is our translatory vector. Okay. So I can simply remove this part to get our previous solution. So if I remove this from this vector, or this is arbitrary vector, means of for all vectors will be in this form. So I am removing this from all these kind of point formats. So what will I get? X here, y here, and if I remove minus 5, I remove minus 5, so it will plus 5 and minus 5, 0. So x plus 2y. Okay. All the points in this form will be inside my subspace. Okay, and what was our translatory point? It was 0 comma 0 comma minus 5. Okay, add this two. Okay, so now again, if you want to write down again it in this way, so you can write this is your z component. And what is z's value? So you can say all x comma y comma z. Okay, where z is nothing but x plus 2y. Okay, you will add in these x y z, you can add this vector 0 0 minus 5 to get your affine subspace. Okay, same here, you can see there is no need to conversion of again. If you want to do to z conversion, or if you don't want, then you can stop here. That's also fine. Okay,
So
same in the next.
basically, we
Yeah,
convert in such a manner so that we can get a subspace, right?
yeah, we are getting the subspace from this. Same for the next one. We can define it in the form of z. So z is removed and x and y are there like this. And this minus 5 is in the third component, and other two components do not have any constant values. So 0 0, and this has constant, so minus 5 is removed. Okay.
Sir, what
Yeah.
about the second? What they say is L is equal to.
This L is affine subspace. It is saying that all the points in this form are inside your affine subspace. Now it is telling you that find out your translatory point as well as the subspace. It is asking about that.
U plus U at the end.
Okay, where? This one.
Yes.
Okay, it is nothing but it is the same thing that I explained here. This
But
U is your subspace. Okay, this U is the x comma y comma x plus 2y. This is, and this is your translatory point. Nothing else. The same solution is given here. Okay. Now, if you want to define the addition and subtraction law, so you are aware that firstly remove this part from this vector that was given here, x comma y comma z, and then apply the addition and then move on. You can see here, if you want to add two vectors in this form, so firstly remove this minus 5 from the third component of both, then add these two vectors. Okay. Then on adding these two vectors, here we have added this part and this part we have added only. This minus 5 is only added once. Okay, x1 is here, x2 is here, so the first component became x1 plus x2. Okay, let me zoom in. Now it will be clear, right? Okay, so you can see x1 here, x2 here, so it became x1 plus x2. y1 here, y2 here as second component, so y1 plus y2 is here. x1 plus 2y1 and x2 plus 2y2, so it is x1, x2, 2y1, 2y2. Okay, and we added this 0, 0, minus 5 once, and then we got this. Okay, same for scalar multiplication. We have all the vectors in this form, so we removed this part. We got this subspace associated with this one. Okay, and then multiplying with c, this L, so we will multiply this part only with c. So multiplying this part with only c, we got this value, and then we added this 0, 0, minus 5. Okay, in short, I already explained. It is just a lengthier way. Okay, so after that it is solutions. So now let's understand this topic as well. So it says that any system of linear equations given in this form, so if b is 0, so this is nothing but homogeneous system of linear equation. So that has already one unique solution, sorry, one trivial solution is always there, that is the 0 vector. Okay, and it is called null space of A. We are aware already this part. Next is this one. If B does not belongs to the column space of A, means if B cannot be written as some linear combination of A, then this have no solution. Okay, third thing is, if B is belongs to this column space of A, then it have a solution, but it can have infinitely many solution or unique solution. Okay, so if it is having unique solution, so its null space will have only one vector, that is this 0, 0, 0. Okay, and if it is having infinitely many vectors, then its null space will have some other vectors other than this 0 vector. Okay, so it is stating the same thing, that if you have two vectors, suppose v is a solution of this part and u is belonging to the null space. So v is a solution and u is null space. So means av will be equal to b and au will be equal to 0. So if I multiply a here, so that will be nothing but av plus au, right? This will be nothing but av is b and au is 0, so b. So this u v plus u will also be a solution of this. Okay, but when unique, so we have only this 0 vector, so doesn't matter how many times we add it to the solution, the unique solution we add it, so we will always get the same value. So that's why it is unique solution. But if it has some other values, so if I add it to any of the solution, then it will give me a new solution.
The column space, the
Yeah,
part
column.
written, yeah, if B belong to a column space of
Yeah,
A,
yeah.
means B and A are same or not same.
B and A are not same. What does that mean? Suppose you have 1, 1, 2, and 3 here. Okay, and here are your variables x and y. Okay, and you have b such as x is 1 and 2, 4, 5. Okay, and this is 7, like this. Okay, so what you can write it as, uh, it is nothing but 5 comma 7 belongs to its null, its column space, means 2 times the first column sorry, 1 times the first column plus 2 times the second column will form the 5 and 7. This is the unique solution 1 and 2. So x value is 1, y value is 2. Okay. And if even suppose these two are zeros and you have this value 2 and 2. So it is still belonging here. X value is 2 and y value is 0. Okay. And suppose if its value are in this form x 1 comma 2 and 1 comma 2 like this. So you have x and y here, and this one is 5 and 5. Okay. So it can have infinitely many solutions. So what you can say that 1 times of this 1 1 and 2 times of this 2 2 will form this, and 2 times or 3 times of this 1 1 and 1 times of this 2 2. So it will be again the same. So it the solution only exists when it belongs to its column space. Okay.
Sir, in this
Yeah.
one, where it's mentioned like, A into V plus U is equal to B. Okay. So, like in this one, this term, this expression basically, yeah.
This one. Okay.
No, no, no. The one above it. No,
A
no. This,
into V
yeah.
plus U.
V plus U. This one.
Yeah,
No,
no, the
no,
one
above.
above it. A into U. A into
A
V plus
into
U.
V plus U.
This
So, like,
one.
what? Yes. What is the significance of this expression? Just
Okay.
wanted to ask.
Uh, what is the significance of this part? It is actually telling that if you are aware of only one solution and you want some new solution, okay. So what you have to do, you don't have to go. If you have the, suppose the vectors, you have this solution, any one solution, and you have the null space span that or the basis for the null space you are having. So you can add that to the solution anytime, and you will get a new solution. That is the thing that is mentioned here. Nothing significance other than this.
So,
This is
basis
only.
for the null space is in AX equal to 0, right? The solution space for
Yeah.
that.
Yeah. Solution space for
All
this.
values of X.
Yeah. So this x, you will find a basis for this, and you can add any scalar multiple of this to this solution, and you will get the answer. Okay, is that clear?
Okay, so you mean to say that V belongs to the column space of A. So we
Yeah.
take any of the vector from that column space and then add it to the vector in the null space. We'll get a new solution. This is what
Yeah.
you are trying to say.
Always. Yeah.
Okay,
Exactly.
okay, okay.
Such that here the null space for this case, these two cases that I solved here. Let me erase the others. So in this case, the null space can be spanned by this vector 2 comma minus 1, I think. Yeah. This will belong to my null space. So if I add this 1 comma 2 as a solution, if I add 2 comma 1, so it will be 3 comma 1 is a solution. If I again add this, then this will be 5 comma 0. It will also be a solution. 5 times 1 comma 1 plus 0 times 2 comma 2. It will be a solution 5 5, right?
Okay.
So is that clear? Now let's continue next. Here is affine mapping or affine subspaces. Okay. So here are some proofs and other things given. So let me give you this insight of this in brief. Okay, instead of going through everything. So basically, what is this? You have a affine subspace. Okay, you have some subspace associated with it. Okay, and you have another affine subspace. Okay, and you have another subspace associated to this. This is A1, S1, A2, S2. Okay, you want to link all this or map the points in this or vectors in this to this part. You want to find out some kind of relation or function to map this. Okay, so what you can say that this affine is nothing but you can write it as some translatory point plus this subspace, right? And here you can simply do the same thing, that S2 plus some translatory vector here. Okay, so it is saying that if I link my this translatory point to this, and I can use the linear transformation to transform this to this. Okay, what I am saying that if I link we know that linear transformation transform a subspace to another subspace, right? We write down the transformation, linear transformation like V2W, we defined like this. This is our vector space 1, this is vector space 2, or subspace 2. So we transform these vectors to this with some kind of linear combinations of its component, and we do. So same thing here. If I use some linear transformation here to transform all the vectors of S1 to S2, and if I transform this T1 to T2, so this T1 and S1, if I take any point in this form T1 plus some V, this V is going to belong to S1. Okay. So if I apply any transformation on this, and it get transformed or it get mapped with T2 plus some point in the S2. V is in S2. So it will be inside our affine subspace 2. This is called linear mapping, sorry, affine mapping. Is that clear?
Oh, sir, please repeat once. I missed it.
We have two affine subspaces. This is our first affine subspace. This is our second affine subspace. And I want my all the points of affine subspace 1 to be linked or mapped with affine subspace 2. So I know that affine subspace 1 is nothing but translatory vector plus some subspace. Same is affine subspace 2. So what I will do, I know that S1 can be transformed to S2 by some linear transformation, and I can transform this T1 to T2 by some other type of transformation. Okay. Or simply if I don't have any transformation here, so I can simply say that this is only needed. This T1 and T2 we will remember directly. We don't need to transform them. Okay. So what I can say, I will write this A1. From A1 I can get this T1, right? From this A2 I can get my T2, the translating vector. Okay. So now I have these four things. Okay, and I want to go from A1 to A2. So what I will do, I will go from S1 to S2 with some linear transformation, and then I will add T2 to every point of this. That's fine. Okay, I will add T2 to get this A2. Then my A1 get mapped with A2. That's the part.
The transformation need not be applied to T1 and T2. I mean, from.
No, no, no. There is no need to apply this transformation over this and this.
I would like to confirm A1 get like we need to just find first of all A1 to S1.
Yeah, A1, from A1 we can get S1 and T1 both, right?
Okay, then T1 also, and from A2 we will getting S2 and T2.
Yeah.
Sir, in
And
this one,
Listen.
let me
Yeah.
from S1 to S2 will
Yeah.
the formation. This
Yeah.
is
We
what
have
we.
what we require is this linear transformation from S1 to S2 that can tell us that transform this, and these two things will be associated with our affine space subspaces. Okay, then our any point in this A1 get transformed to some point in this A2. Okay. Yeah.
sir, if I may.
Yeah.
Sir, so basically in this one, so sir, we don't have a direct transformation from A1 to A2 as such, right?
No. Yeah. We
Because
don't have.
because from
That is
S1
the
we are,
major doubt.
yeah, from S1 we are getting S2, and then from S2 we are getting A2, right?
Yeah. Exactly. Any other doubt?
So we need to calculate the transformation matrix, or it will be given to us
Transformer matrix. I don't think it is needed here.
from
Okay.
S1 to S2.
Yeah. It will be simple questions based on this.
Okay, okay.
Not that hard. Okay. So this is the part. Now look at this example. Here it is saying that you have some affine subspace in this form x comma 1, another affine subspace in this form. Okay, so you can directly conclude that it's a translating vector 0 comma 1, right? And all other points will be in this form x comma 0. From this you have already calculated that 0 0 5 is the translatory vector plus x comma y comma 0 will be our subspace, right? And if you want to map, so you want to map this x comma 0 to this part. Okay. So what you can say that you want to map, so this x will go to this x, right? Or in simple, you are here, what I can say, all the points in this form x comma 0, you want them to be linked to some R2 space. Sorry, it is a part of R3, but you have only dimension 2. So you want to two dimensions here, one real number here, another real number here, that do not have any dependency, or they can have. Okay, it is not given. So we have one dimension here. So what I can say that x comma 0, suppose I write any linear transformation I can write. So I am writing x comma uh, x plus 5, sorry, 2x comma 0. Okay, I can write this. I can also write this x comma 3x comma 0. I can also write this x comma 0 comma 0. Okay,
So
but don't put any constant values here, because constant value, what way they will do, they will not let it to be a subspace. It will become affine subspace then, if any constant value is there, right? It will not pass through the origin, it will start passing through somewhere else. So that's why we can't use any other values like that. Is that clear? So if I want to find out now, suppose 5 comma 1, where it will be linked. So suppose I am taking this one, this linear transformation. So firstly I convert it to 0 comma 1 plus 5 comma 0, right? Now no longer I need this, I can remove this part. Okay, 5 comma 0 I can transform using this transformation. It will be transformed into 5 15 0, right? And then I will add this 005 to this, so it will become 5 15 5. It is an image of this part. This is the thing. Is that clear?
So there is no restriction on that the
Linear
3D,
transformation.
yeah,
Uh,
transformation. It just need to uh, follow that subspace thing. That's it.
yeah, it is asking that it is an affine subspace. Then tell us that is there any linear transformation existing. So we can take any linear transformation here in this question specifically. Okay. In other way, in other questions, maybe it is given to us. Okay.
Yes, sir. Yes, sir.
Next is here. So you can tell me for this linear this affine mapping, that x y z, we have mapped it to this. Okay. So for this vector x y z, can you tell me that what will be my translatory vector? Is there any constant term in any of the component?
The second component.
No, there are no constant terms.
So three, no?
Where is 3? It is not 3, it is z. X, Y, Z is there. So I am using this X, Y, Z. Okay.
Uh,
Not, I am not talking about the range. I am talking about the domain.
no constant term is there.
No constant. So I can say that it has a translatory point that is 0, 0, 0. Right? So I can remove this part and it will remain like this. Now let's look at the range space. So what is this? It is having 2x plus 3y plus 2, right? Next one is having 4x minus 5y plus 3, right? And next one, no, only two values are there. Okay, because it is in R2. So now can you tell me that what will be the translatory vector in this?
2, 3.
2 3.
2 is here and 3 is here, right? And what will be my subspace look like?
2x plus 3y. 4x
Ey,
minus 5y.
x minus 5. Yeah, that's all. So
So
you have to
why did
find,
we go for domain first? Do we need that for domain also?
because it is a fine subspace. So I already said that we need this subspace out of it.
Okay.
Okay, okay, yes, sir, yes, sir.
Okay.
I
Okay.
said that you require. Same for A2, we require this S2 as well. So now we found these two vectors. Okay. Now we will find some relation between this or linear transformation from this to this. Okay. So you can see It is a linear transformation of this vector to this. We are using x and y that are the components of it, and we are using their linear combination to get its first component as well as second component. Okay, so that's why it is linear transformation. So yeah, it is an affine mapping. Affine mapping. Okay.
Sir, in
Yeah.
case, just like in the first check you did, you
Yeah.
took out the 000, okay, from XYZ. So
Yeah.
in this case, say for example, it would have been, I'm just saying a
Yeah.
random thing. If it would have been x plus 2, y plus 1, and z plus 3.
Yeah.
Sir, what would have been the approach? If
So you will same remove this part like this,
one,
that x
one, two,
plus
three
1,
will,
2, 3
okay,
is there. So 1, 2, 3 you will remove. Right? Okay.
okay,
But when it is R3, so in domain mostly we don't need to remove, because suppose this is my space. Okay, complete two-dimensional space I am taking. Okay, suppose I transform this point to here. I translate this. Okay,
okay,
so this point get translated to this point, this. Okay, and the point that is here I will translate it here. So means this complete space is translated somewhere there like this. So still it is covering the whole R2. Its translation cannot be observed. It is still covering. So if it is a complete vector space, then there is no need for translation. You will always get this zero kind of things. But if it is given some constant in these values, then do this. Okay, then you can remove the vector. Okay.
sir. So okay, okay. So since we will get, say for example, in this case we are getting 1, 2, 3 outside.
Yeah.
Then sir, in that case, like
The
don't we
answer
have, yeah,
in that case, we still have to find out this 1, 2, 3 will be here. So means firstly, if I take any vector, so I will remove this 1, 2, 3 part. Then I will apply this transformation, and then I elevate, and then I add 2 comma 3 to it to get its image.
okay.
Is that clear? Anyone else having any other doubt?
So we don't have to find the f of 1, 2, 3, right? In that case.
No, no, we don't have to find out. Or
Mm.
if it is given that you have to find out f1, 2, 3, then that will be nothing but this one part. You can say that this
Okay,
transformation of this.
this constant would lead to transfer this 2 comma 3. Some if it
Yeah.
is given like that.
If it is given like that, you can say that this is transformed to this part. Okay.
Okay, okay.
Here you can see again one example is given. So it is asking the corresponding subspace of R3 that is related to this affine subspace. So we have XYZ in this form. So we know that I want my, I can remove one of the variables. Suppose I am removing, which one I should remove? Suppose X I am removing. So X will be, look like 6 minus Y minus 2Z, right? So I can put X value here. So I got all the vectors in this form, 6 minus y minus z, 2z, sorry, 2z, comma y, comma z, like this. So from here, you can see what is my translatory vector. It is 6, 0, 0, right? Okay, then I can add the remaining subspace part, y minus 2z, y, and z. Okay, so I can again put this value as x, and what will be the x value? X value will be minus y minus 2z. Okay, or I can say that x plus y plus 2z will be equal to 0, right? So this will be my subspace, this one. Okay, is that clear? Okay. So next is this question. This is a little bit confusing if you look at this part. So basically, it is saying that which of the following represent is associated with an affine subspace. Okay. So suppose I have, what are the solution for this case? Let's leave these three parts I'm leaving for now. Let's continue with the fourth option. you can see that it is some linear transformation given, not linear transformation. If you find out the value of y here, so you will get 1 minus 3x. So all your point in this form, x comma 1 minus 3x, will be inside your affine subspace, right? So what will be my translatory vector here? 0, because this has no constant term. And what is this having? 1. I can write 0 comma 1 plus x minus 3x. Okay, so I want to write down it in this form x and y, so I can put this value y here. So what is y? Y is equal to minus 3x, or I can write y minus 3x should be equal to 0. Okay,
So y
so
plus 3x.
sorry, yeah, y plus 3x. So x comma y, where x plus 3x plus y is equal to 0. So it is a subspace with this. So this is a linear, sorry, it is an affine subspace. Same for this, and same for this one. Okay, here you can see this is x square. Okay, so it is already quadratic, we want linear transformation, so that's why it is removed. Cubic, removed directly. X 1 comma 2. So what is the translatory vector? The translatory vector is 1
0
comma
comma 0 plus 1 comma 2.
0 comma 0. It is our subspace.
Yes.
Okay. It is our translatory vector. So this is also true. But what about this case? This one. These two have 2 power and 5 power, that's fine. But about this, because it has only one solution, and that is 0 comma 0. Okay. So what will be its translatory vector? It will be again 0 comma 0, right? This is our translatory vector. It is our subspace. So this is a subspace, right? Yeah, it is following every property of subspace. So that's why it is affine subspace. Their combination will form an affine subspace. But if you look at this part, this one, second option, x square plus y square. So x square plus y square is equal to 4. Okay. So it can have many solutions. Suppose it can have 2 comma 0 is a solution, right? And 0 comma 2 is a solution. Okay. If you add these two vectors, okay, or if you plot the graph for this, let's plot the graph. Okay. Then you will get more clear details.
So it will be a circle.
Circle.
It will be a circle. Yeah, I'm aware of that thing. X raised to the power, where is this? X square plus y square is equal to 4, right? This one. So, can you tell me that is there any, even if I translate this whole part, even if I translate anywhere, okay, if I take this circle from here and I will move it here, okay, here, this is the circle, this is the circle, okay. So, is there any way to represent the subspace related to it? There is no subspace. First thing that we want any one of the point to pass through the origin, because origin is necessary for subspaces. Okay, with the standard addition and multiplication, so we require the origin. If I shift this part to this part, okay, so it will again be a circle. And if it is a circle, still it will be a circle. Okay, every point, if I translate, translate this point to this part, okay, and so this point will be translated here, this point will be translated to here. Okay, so still it will be a circular shape. Okay, means if I translate it, let me write this part, x minus 2, right? And here I will write y minus 2. I translated not y minus 2. I should write something else. Yeah, it is okay. This is fine. It is passing, it has 0 vector, right? But if you look here, that if this is a subspace, then there are any two vectors. If I take this and this, so their linear combination or their addition should follow the additive closure property. Means their addition, if I add these 2 points, so the result I will get should also be inside the subspace. So their result will be this part, 4 comma 0. It will be not this 4 comma 0. So this one. Okay, this is inside. Yeah, that's fine. But if I add 4 comma 0 to 4 comma 0, so it will be 8 comma 0, right? But it is not inside this subspace. If it was a subspace, it is not following the properties of subspace. So that is why it is not an answer. Okay, it is not going to be an affine subspace. Is that clear?
Yes, sir.
Next thing what I can say, that if x square plus y square is this 0, you can see this is only this point. Okay, so that's why it is already a subspace. So we can say that it is an affine subspace as well. Okay, means each subspace is a affine subspace, because we can add the zero vector. We can write the zero vector is the translatory vector, and it will be an affine subspace. Here x raised to the power 5, you can represent these graphs and you can get your answer, right? Okay, should I continue? Next part is this one, where you are given U be a subspace of R3, where basis of U is given by this. This is the set that is having all the vectors that are inside the basis. Is an affine subspace. Okay, it is asking that which one will be the affine subspace of this subspace. So this subspace will be formed when I do the linear combination of these two vectors. Okay, means x time if I add my first vector to the second vector, y times of the second vector. So all the points in this form x y minus 3x minus y, okay, will be inside my subspace, right? And I can translate it to any part. So you can see that with this equation, what will be my subspace related to this? So my subspace related to this will be all x, y, and z, where x plus 3y plus z will be equal to 0, right? Okay. For this one, it is already a subspace. Okay. And here it is a subspace. It is an affine subspace. Okay. But we need to check which one is exactly matching with this. So in this case, you can see x is x, okay, y is y, but z is minus 3 minus x y. So if you add, if I can rewrite this equation as 3x plus y plus z is equal to 0.
But that is 3y, sir, right, sir? In the option.
3x, 3, just a minute. Let me check this. Okay.
Excuse me, sir.
Sir,
Yeah.
it
Sir,
should be
at the
minus.
first, in the first step, when you at where you write x into vector one and plus the
Yeah.
addition is y x minus 3x minus y, isn't it?
Yeah, minus 3x minus y, your third
No, no,
component.
no. First one is y, and then second one is x.
Yeah. This is okay. So simply, okay, let me do one thing. Instead of x and y, it is confusing. So let me use some other thing. I will use
A, B.
A and B. Okay, then it will be easy. So this is B, this is A. Thanks for answering. Minus 3A minus B it is. Okay. So from here, if I compare these values now, if I compare these values now, so it will be my vectors all in this form x, y, and z, where x is equal to b, y is equal to a, and z is equal to minus 3a plus b. Sorry, minus b. Okay. So x value is b, so I can replace this b with minus x. Y value is a, so instead of a, I can write minus 3y. So this equation z minus 3y minus x, I can rewrite it as x plus 3y plus z equals 0. Okay. So this part, it has this subspace associated, and this is looking like this, right? So this is affine, that's fine. And here the subspace itself is given. Okay, so we can say that it is 0 comma 0 comma 0 translatory vector, and we put this. So this is a subspace, it is correct. In this one, you can also see it will also have the same subspace. Its corresponding subspace will look like this one. So that's why
Sir,
option 4 is also correct.
sir, even option two. Oh, okay, 2z, 2z. Okay, okay, fine, fine. Okay.
2Z it is there. Okay, so that's why it is wrong.
No, no, understood, understood.
Sir, what would be the translatory vector in this case? First option and fourth option.
In first option I am telling, after that you can continue with the for other options. Okay,
Yes.
so you can put x plus 3y plus z is equal to 0, sorry, not 0, 3. You can find out any one variable value. Suppose z value I am finding, so it will be 3 minus x minus 3y, right? Okay, so I can substitute this value as x comma y comma 3 minus x minus 3y. So the translatory vector from this you can get 0, 0,
I got it.
right?
Basically, in this one, you have put x and y as 0, 0, right? Basically.
Yeah, x and y I put and I got z value. One more thing, that translatory vector is not, I already told that it is not unique. Okay. In the earlier case when x comma 1 we used, so I said that 0 comma 1 is also working and 2 comma 1 is also working in this case, if you can recall. So here, instead of a z value, if I have find out x value, so it will be minus 3 minus 3y minus z, right? And if I put, then it will look like x minus 3y minus z,
Okay,
comma
in this
y
case, it will be
comma z.
different.
In this case, it will be 3
3 comma
0
0,
0.
0.
Okay, it is not unique. That's all. Okay, let's. Next is this one. In this, you can see that three equations are given here. Okay, let me erase the other parts. Is that clear that why it is not unique and that part? If you are not getting, then I can explain it again. No? Okay. Then let's solve this question. Okay, so here it is given, it is asking that the solution of this part. So you are aware that how to find out the solution. Okay, you can simply write down it in augmented matrix format. 1, 1, minus 1. Okay, minus 1. 1, 1 minus 1, 1 minus 1. Okay, and here 1, 0, 1, 0. Okay, so from here I can do R2 plus R1. I am adding R1 to R2. Okay, and then what I am doing, I am also adding R3 plus R1 I am doing. Okay, so I will get minus 1, 1, minus 1. Here I will get 0, 0, 0. And here I will get 0, 1, 0. And here I will have 1, 0, 0. Right? I
One,
can
no, sir.
multiply.
101.
Yeah, yeah, this is 1. Right, right. So what I am doing now, I am multiplying my R1 with minus 1. Okay, so it will become positive, negative, positive, negative. So from here, this is my pivot element, this is my pivot element. Okay, so this
So we can do one more time R1 plus R3 so that it will reduce the number of variables.
okay, you can do that thing. Okay, that will also fine. R1 plus R3. If I add R3 to R1, so it will become 0 and this will become 0 as well. Okay, so now we have x plus z equals 0 and y equals 1.
Yes.
So y value already we got and x is the dependent variable. So I can write x is equal to minus z. Of z. So you can see the last value is t in some cases. Okay. And one case we have minus t. So let's first put value t. So what will be my x value? X value will be t, sorry, minus t, and
Yes.
y value will be 1 and z value will be minus.
So T, no?
Simple.
T.
Yeah, simple t. Yeah. So this option we got correct. Okay, now in these two options, minus t, sorry, one option is there only with minus t. So if I put the z value minus t, so it will be minus t, it will be 1, and x value will be t.
Yes.
This one. So is it there? No, it is negative t already given. So this is wrong. Okay. Next is this question. This is a little bit confusing, might be, but not, I think. In this one, you are given some affine mapping. Instead of giving you the linear transformation or anything else, they just give you some uh, mapping directly that f2 comma 3 is mapped with 3 comma minus 1. So now here is a problem that first thing it is this R2 is completely taken. So I already said that I can choose the translatory vector in this case of my choice. So mainly we choose the origin. Okay. So means I can think that this transformation, I need to find out the subspace, okay, on which the linear transformation is going to work. So if my transforming vector is 0 comma 0, translating vector, sorry. So my subspace will have this 2 comma 3 vector, right? The subspace associated with this will have this 2 comma 3 after removing this 0 comma 0. So I got this. So it will be inside my subspace. Same for this 2 comma 1. It will be inside my subspace, and same for 1 comma 0. All of them are inside my subspace.
Sir,
And I
sir,
want,
sir. So
yeah,
from subspace you are removing 0 comma 0, then how, it will no longer remain the subspace, no sir.
listen. It is affine subspace.
Okay.
Okay. From this affine, I am removing the translating vector, and then I am getting these vectors. Okay. So these are all part of some subspace.
But in previous examples, it was not necessary that 0 was part of that affine subspace, no sir. In this case, are we assuming it to be part of that subspace? 0 0.
I said that the translating vector is not unique.
Correct,
Okay,
sir.
not unique. Okay. So
Hmm.
I said that if the translating vector is not unique, what I can do, who's this one, Shani? So translating vector is not unique. So means I can take any vector inside this affine subspace and call it as affine translating vector. In the case x comma 1, when I said, so it has 2, 0 comma 1, it is also belonging to this, and 2 comma 1, it was also belonging to this. I can take any vector. Okay.
Sir, please proceed. I'm a bit confused, sir. I'll ask it later.
Okay. So I got this. So now I need some linear transformation. So suppose G is my linear transformation on these points, that is transforming 2 comma 3 to some point, some point. And then I added the translatory vector to it, and I got 3 comma minus 1. Same here. When I transform this 2 comma 1, I got 1 comma 2, and I added the translatory vector, and I got 1 comma 2. Sorry, not 1 comma 2. I got some value here. Okay. Same here. I transformed it and I got some value. I added the translatory vector. I got the value 0 comma 1. You can see 1 comma 0 is linked with 0 comma 1. This is with this with this. Okay.
Sir, uh,
Yeah.
just wanted to ask you something. Like, I don't know if my understanding is right or wrong, but so the moment you said you are removing the zero
Yeah.
from this 2 comma 3, right?
Yeah.
Like, because anyway 0 plus 2 comma 3 will always be 2 comma 3, right?
Yeah.
So like, what is the importance of removing, specifically removing the 0 0?
No. I just told you that I am not removing anything, but I told you that if it was a fine subspace and it is not R2, it is belonging to a two component vector. Suppose there are vectors uh, such that x comma 1
Okay,
like this. Okay.
okay, okay.
So then you are using the mapping. So you have to remove the 0 comma 1. So same way we are not given this. This is y now. So I took 0 comma 0 and I removed just to get to the subspace. Okay, it is just some, it is not necessary here because already we are taking the complete space. So that's why, but in order to tell you the method exactly what you should do, so I did that. Okay.
Sure.
Yeah. So we know that whatever be the value here, so it is that two component vector. So it will have some two values. Suppose x1, y1 are there, and x2, y2 are there, and x3, y3 are there, right? So this x1 will be some linear combination of these two, as it is a linear transformation, right? And same y1 will be some linear combination of these two values. Okay. Same linear combination will apply here to get this, but now the values are 2 and 1. Same linear combination will apply here and we will get this. Okay. What basically I am stating here, that first of all, let's see that this my translatory vector is nothing but it is some x comma y. Okay, let's continue with this. So whatever my linear transformation I will get, okay, so I can write it as 3 minus translatory vector minus translatory vector minus translatory vector, right? I can write like this. This is the linear transformation that I am doing here. Let me remove this part. Okay, now it will be clear to you. Don't use these variables. Okay, just directly understand. So what I am doing, I am transforming. I am using some linear transformation and applying the linear transformation on this vector 2 comma 3. I got another vector. Same here. I got another vector. I got another vector. Okay, and this vector will be equal to when I remove this part, this translatory vector from this and this. I am unaware of this translatory vector, so I took x and y. Okay, some point x comma y. So I can write again. This will be some x comma y, and x comma y. Okay, so this is nothing but 3 minus x minus y, 1 minus y. Okay, it will be 1 minus x. Okay, and 2 minus y, and it will be minus x and 1 minus y. Is that clear up to this part?
Sir, is there any like rule, because here all these three x and y, they will be same, right?
Yeah.
So like, do we have to follow it? Like, is there some specific restrictions that we have to take this only?
Yeah, the restriction is there or not, but the only thing is this that whatever the value you are subtracting here, I said that we are subtracting 0, 0. Okay, so I said that when you apply this transformation on this or the affine mapping on this affine mapping, so it will give you this some vector. So
Uh,
every time you are removing this 0, 0, so you will all time give it this.
Understood, understood. So, sir,
Okay.
basically what I'm doing is because when I'm doing this transformation, say for example, g of 2 comma 3, we are getting this x and y, right?
Yeah,
So, but even for g of 2 comma 1 and g of 1 comma 0 also, we are getting this x and y.
yeah. Not G. We are not getting this part. Okay, when I am applying F on this, so I got this part.
So we actually wanted to remove that xy part, then apply that transformation, na?
Listen, what I said that this is our domain, this is our codomain. Okay, here is our affine one. Here we have affine subspace 2. Okay, so I removed the translatory vector that was the 0 vector, 0 comma 0. Okay, so I got some vector, sorry, subspace S1. Okay, in this subspace, I have these 3 points. Okay, whose image I am aware of. Okay, so its image is inside this S2. Its image is inside in S2 and here it is. Okay, all the images are inside S2, but I am given its affine subspace, sorry, affine image. So I have to add the translatory vector here.
Which is 0, 0.
No, here it is not 0. This was 0. We considered it because all the completely R2 we are uh, having. So that's why we use this. But now it will be some kind of affine mapping that is given here. Based on this, this will be defined.
Okay.
So that's why F00 was linked with this. Means you can see that the 0 vector, suppose S1 will have this vector, right? 0 comma 0. Consider this part. Okay. So it will be mapped with, if it is a linear transformation we have, so it will be mapped with zero vector of this space, right?
Yes.
Okay. But then we added some
X and
translatory
Y.
vector to it.
Yeah,
Okay.
yeah.
So we got this x comma y here. Okay. We removed this 0 comma 0, but still we did this, then we got this. So that's why I said that this, the transformation of this, the affine mapping of this will be this. Affine mapping it is. It is not linear transformation of this. Okay.
The
Linear
linear
transformation,
transformation would be the zero vector
zero,
in,
yeah, the zero vector.
but to that we are adding that translatory vector.
Yeah. Then we added the translatory vector to get the affine mapping.
Fine. Yes,
Of,
yes.
okay. So that's why it is. Is that clear?
Yes, sir.
So now we got these 3 points here, and we know that these 3 points can be formed by some linear combination of these components. Means my first component, suppose the linear transformation that I am applying, suppose the linear transformation of any point a comma b will look like lambda times a plus mu times b. Okay. Or let me use some other variable, otherwise they will look like really boring. Okay. What should I use here? Suppose any point I am taking p comma q. So their linear transformation, if I am doing, so it will be something like a times p plus b times q here, and c times p and d times q. Because in linear transformation, we just do, what do? We just find out some linear combination of these components and define it. We want a vector in R2, so we defined like this. Is that clear?
Yes, sir.
So now let's write down the our above parts that are given here. Okay, g of 2 comma 3 is given here. So in place of p and q, I will put these values. Okay, so it should look like 2a plus 3b,
3B.
right? And here it should be 2c plus 3d, right? Same here, g of 2 comma 1, if I have to find out, so it should look like 2a plus
Plus B.
b, 2c plus d, right? And same here, g of 1 comma 0 should look like uh, 2a plus 0.
So A now. A plus
Yeah,
0.
yeah, 2, yeah, not 2, right. This should be a, and this will be c. Okay, but their linear transformation we already figured out. It should look like this: x and y, where these are the coordinates of the translatory vector. 3 minus x, let me write down here. It is 3 minus x minus 1 minus y, right? 1 minus x and 2 minus y, right? 1 minus x and 2 minus y. And other one, minus x and 1 minus y. Minus x, comma 1 minus y. Okay. So from here, you got this. And now, if you compare, so you can see how many variables we are having, a lot of variables. Okay, so let's leave it. So let's compare only the the first component, this part and this part. So we got equations: 2a plus 3b is equal to 3 minus x, right? And 2a plus b is equal to 1 minus x, right? And a is equal to minus x. Okay, a value I got as minus x. So can I put it here in this equation, second equation? So it will become minus 2x plus b will be equal to 1 minus x. From here, I will get the value of b. What will be that? X plus 1, right? Now a value is given, b is here, so I can put it in this one. So what will I get here from this equation? Twice of a means minus 2x plus 3 times of b, that will be 3x plus 3. It should be equal to 3 minus x. Okay, from this equation, what I can say, minus 2x plus 3x, it will be x, and this minus x will be there. So 2x is equal to 3 cancelled out, 0. X value I got from here, 0. Okay, you can see x value is 0. So I got b value as 1 and a value as -1. You can use the Gaussian elimination method and that thing if you want to. Okay, you can find the solution of this by that method as well. So a value I got, b value I got, and x value I got. Now let's take the second components of these parts, this one and this one. Okay, so this is 2c plus 3d is equal to -1 minus y. Next is 2c plus d, that is equal to 2 minus y. And next is c is equal to 1 minus y. Okay, from here c value is, we can find out c is nothing but 1 minus y, right? Already given. So I can put the c value in this equation second. So what will I get? Twice of 1 minus y plus d is equal to 2 minus y. I can rewrite this equation as 2 minus 2y plus d is equal to 2 minus y. Okay, I can rewrite this equation as y is equal to d. Okay, or in easier way, d is equal to y. Okay, c and d value we find out in respective of y, so I can put these values in this equation. So what is c? Sorry, 2 times c will be 2 minus 2y, right? And plus 3d, 3y is equal to -1 minus y. So from here I got uh, y plus 2 is equal to -1 minus y. So if I add 2y is equal to 3 and y value, sorry, -3, y value will be -3 by 2. Y value is -3 by 2, then d value also be -3 by 2. And what will be my c value? It will be 1 minus -3 by 2. So that will be nothing but 5 by 2. Okay, is that clear?
Yes, sir.
We did nothing. We just, up to this part, I wrote that how to define linear transformations and just compared these values. There are 6 variables and 6 equations I am having. Okay,
Sir,
not 6, 1, 2, 3, yeah, 6 variables and 6 equations I am having. So I solved this and I got the value of a, b, c, d, and x and y.
sir, would you
Yeah,
mind just going above once?
above.
Oh yeah, this one. Yeah, yes, yes. So in
Yeah,
this one, actually, sir, I was only confused with this x and y basically. Sir,
yeah.
this x comma y. So like in this translation, like from A1 to A2, where is it exactly playing the part?
Sorry, I didn't get.
Sir, like in this translation, right, from A1 to A2, we are
Yeah.
getting from S1 to S2. So in this part, like where this X and Y is coming into play? That,
Okay,
like,
it is coming here. When at last, when this S1 transformed the point to S2, then we added this X and Y.
okay,
Okay, linear transformation can transform a subspace into another subspace, right? But we want affine subspace here, so we added this XY.
okay, okay. So
Okay,
we add, okay. So we added this add X and Y to 3 comma minus 1. Okay,
okay, not 3 comma minus 1. We added it to this linear transformation that I got. I added here X and Y.
okay,
Okay,
okay.
so I can remove it from this part. Okay.
Basically, we are trying to equate two subspaces by removing the affine part,
Yeah,
the
yeah, yeah,
translatory part.
exactly. Yeah, we are just comparing these two parts. From A2, we removed this part, and from A1, we removed this part, and now we have only this. So we are comparing these parts. But we also have to find out the value of this. Okay, X and Y. It will be needed. So from here, it is given. So finally, I have to find out A and B value, that is f of -2 comma 5. So if I write here f of -2 comma 5. So you know that I have to remove the zero vector firstly. So it will be linear transformation now, g of -2 comma 5, right? So this linear transformation can be explained as ap, if p comma q I want to find, so a times and b times. So what was the value of a? It is -1 and b is 1, right? Wait a minute.
So
It should be
B is
0.
1, A is -1. 0.
It should be 0. A should be 0. If x is 0, then minus x is also 0, right? That's the problem. Okay. So a is 0 means a times of this minus 2 plus b times of this. B value is 1, so 5 times of this. This is my first component. And what will be my second component? C times p and d times q. So c value is 5 by 2. 5 by 2 times this minus 2 minus 2 plus uh,
3
d
by
value
2.
minus 3 by 2. Okay, so minus 3 by 2 times this 5, right? This will be my linear transformation. So that is nothing but if I add this part, so I got 5 here and 5 minus 15 by 2, right? Yeah. So that will be nothing but 5 comma minus 5 by 2. Okay.
Sir.
Yeah.
So shouldn't it be minus 5 minus 15 by 2?
Just a minute. Let me check. It should be minus 10, minus 15, minus 25 by 2. It should be right.
Yes.
Minus 25. It should be 5, 5 minus 5.
Minus over there.
It should be negative. Yeah, it is negative. Minus 25 by 2, right? Okay. So I got this. Now I have to add. This is my in subspace 2. It is inside. Now I have to add that x and y. What was my value of x and y? X value is 0 and y value is
Minus
minus.
3 by 2.
Okay. So I will add 0 comma minus 3 by 2. So if you add this, so you will get 5 here, and if you add this to this, so you will get minus 28 by 2. So its answer is 5 comma minus 40. Okay. So in the question, it is asking a plus b. So if you go here, so 5 minus 14 is minus 9. The answer minus 9. Is that clear?
Yes, sir.
A little bit lengthy, it is right.
So is there any shortcut way?
No, this is only one question related to this. Okay, so don't worry. Okay, so that's up to your affine subspaces. That's all. And now we will move on to the inner product spaces. Okay, so any confusion you are having related to this, then you can ask. Otherwise, I will continue to the inner product spaces. Okay, that is this is up to this part. All your other things are covered. After this, you will not see these subspaces and this thing. A little bit maybe you will see. Otherwise, next part is calculus mostly. Okay.
So how many questions will be there in the exam, sir,
Affine
regarding
sub
this?
only lesser amount of this. It doesn't cover a lot. Most weightage is from the multivariable calculus, but cover it. Okay.
So quiz
Not
to
that.
week 4 to 8, week 5 to 8.
Yeah. Week 5 to week. No. I think week 1 to week 8, all concepts are there. I think. Once check it. I am not aware completely. I will check. Okay. I will check. Then I will tell you in the
Mostly
next session.
in a
I will.
quiz one topic will cover from 1 to 4, then quiz 2 for 5 to 8, and
Yeah.
end term will be 8 to 9 to 12 like this.
No. In end term, all the syllabus is there.
The whole syllabus will be there, right?
Whole syllabus is there, but question most of the questions
Yeah,
belong to eight.
mostly, yeah. Most probably you will get from that part, right?
Yes.
In quiz two, same. In quiz 2, you will get most of the questions from 5 to 8. And in end term, you will get from the last part. So now let's start. Dot product. Dot product. How do we find out the dot product? Maybe all of you are aware. Here in this part, it is not a lengthy topic. It is easy, very easy. So firstly, we will understand two things. Dot product. What is dot product? What is length of a vector? Three topics we will cover. Okay, length of and angle between two vectors. So dot product is basically defined as if you have a vector like this in 2 dimension. It is so your first vector is x1, y1, and next vector is x2, y2. Okay. So how do you define the dot product? So firstly, multiply this first component with first x1, x2. multiply the second component with second one. Okay, and if it has more than this, suppose it is not two-dimensional, it is n-dimensional vector. Okay, or n components are there. So this is x1, y1, z1, w1, u1, and so on. Okay, z1, w1. So what you will do? Sorry, 2, 2. So x1, y1, y2, no, y1, y2, z1, z2, and w1, w2 means corresponding parts you will multiply and then add all of them. Okay, so this will be your dot product if components are given. Okay, how to find length of a vector means suppose you are given 1 comma 2 and you have to do the dot product with 3 comma 4. So it will be 1 times 3, that is 3, 2 times 4, that is 8. Add these two values, so you will get 11. It is your dot product. Okay, now what is length? Length you can define as a square root of any vector's dot product with itself. If you do the dot product with itself, then you will get the square of length. So you have to do a square root as well. Suppose you want to find out length of this 3 comma 4. Okay, so you will do the dot product of 3 4 with itself. 3 4. So what you will get? 9 here, 16 here. Add these two, you will get 25. So it will be equal to square root of 25. That is 5. It is 5 unit of length. Okay. Next thing is angle between two vectors. So angle is defined as, suppose two vectors u and v are there. Okay, length, how do we write? It is right, I wrote it like it length. What is the short way of defining? You can write like this. Okay, this is the magnitude or length, whatever you call. Okay, so angle is defined as u, or simple, let me use the simple single lines, single vertical lines. Okay, u dot v. Okay, this is the magnitude of u or length of u. This is length of v times cos theta. So here this theta is actually the angle between them. It is equal to u dot v. If you do dot products of two vectors, so basically it is equal to this. So from this equation you can get the cos theta value, and then you can get the theta value. Okay, this is the only part in this. Then we will move on to the some other things we will see, like the norms and other things. Okay, up to this part, is that clear? Three things you need to keep in mind: dot product, length, and angles. Anyone having any query related to this? No? Okay. So here you can see dot product is given between these two, 2 and 3 multiplied, then 4 and 5 multiplied, and then we added these two things. So 6 and 20, we got 26. Same for three-dimensional vectors. The length is here. You can see 3 and 4 we did multiplied, and that's all. Okay. See here, if you have to find out angle between these two vectors. So what I said, that u dot v, do the dot product between them and write magnitude of u times magnitude of v cos theta. So u dot v, what will that be? It is 1 0 0 and 1 0 1. So if you do the dot product, means multiplying corresponding elements and then adding. 1 into 1 is 1, 0 into 0 is 0, 0 into 1 is 1. Add all these components, so you got 2. Okay.
Sir, one,
Zero into one
zero
is zero,
into
sir.
one.
Yeah. 1. Sorry. 0 it is. Okay. So 1 it is. So you got value 1 here. So now find out magnitude of u. How can we find out? By finding out the dot product of u with itself. 1 0 0 dot product with 1 0 0. So what you will get here, 1 0 0, and the add of these values is 1, and do the square root of this. Okay, so that is 1. Same for v. The value is 1 0 1, 1 0 1. When you do the dot product, you will get 1 here, 0 here, 1 here. Add these values to do the square root. So root 2 cos theta. So from here, cos theta value you got as 1 by root 2. So you are aware that cos theta's value 1 by root 2 is when the angle is 45 degrees. So theta is equal to cos inverse of 1 by root 2, that is 45 degrees, or pi by 4 radians. Are you aware of these trigonometric functions and these things? Anyone having any issue with that? You can tell me. Okay. Same here, one another question is given 101 and 011. So if you do the dot product of u and v, so what you will get? 1 times 0, 0, 1 times 0, 0, 1 times 1 is 1. Okay, divided by magnitude of u, magnitude of v. So magnitude of u will be root 2 and magnitude of v will be root 2. So it is nothing but 1 by 2. It is the value of cos theta. So you know that cos theta value is 1 by 2 when theta is equal to pi by 3 at 60 degrees. Right? So the answer is pi by 3, this one. Next is given here some questions like this. So I am going to solve this one and the rest you can solve by yourself. If you have any problem, then you can tell me. So here you are given three vectors, sorry, four, u, v, w, and s. Four vectors are there. Okay. And you are given their dot products and some of the vectors. U is a vector ABC. So it is given that u dot v. So u is a vector that is A, B, C, and v is a vector that is 1, 2, 3. You are given their dot product. Their dot product will be A plus 2B plus 3C, right? It is equal to 1. It is given. Next is given that dot product of U with W is minus 1. What is W? W is 1, 1, minus 1. So if you do the dot product, you will get A plus B minus C is equal to minus 1. Okay. Next is use dot product with S is given. So what is U? ABC. And when you do the dot product with S, that is 101, you will get A plus C is equal to 0. So you got three equations. Now you can solve it by yourself. Okay. And you will get your answer. Same you can solve the other parts as well. Okay. If any question you are finding hard, then you can tell me. I will explain that part. Is that clear
Sir,
up to this? Yeah.
how can we reach out to you on Discord, sir? Your
Okay, you can write on discourse. My Gmail ID is 23F1002 760. Okay, you can search for this roll number.
23F1002 760.
760. You can yeah, you can tag me. Then I will explain. Okay. Next is inner product on vector space. So now let's consider the inner product. Till now we have seen the dot product. Okay, length and angle. Three things were there. Same we will continue for this part. Angle might not be there, but length and dot product will do. In case of inner product are manually defined products. Okay. So inner product is nothing, but this dot product we are aware of the standard method, but inner product are some other types of methods. Length, in case of inner product, we don't call it length, we call it norm mostly. Norm kind of thing or something else, I think. Let's check what is that. So let's continue. So what is inner product? Inner product must satisfy these four properties. That if you do the inner product with itself, then it should be greater than 0 always, except this case when your v is 0, when your vector is a 0 vector. Okay. Next thing is this, it should follow the distributive property. It should follow the commutative property. And it should follow the scalar multiple property. Three properties. Okay. So it is asking, is dot product an example of inner product? Yeah, you can check that for any vector, suppose we are taking in 2 dimension, okay, R2. So AB we have, And if I do dot product with AB, so I will get A square plus B square. This is a positive term always, and this will be positive term always, right? Except the case when both A and B are 0. Okay, then only we will get this value 0. So means this value is 0 only when A and B are 0. Otherwise, it will always be greater than 0. So this property is satisfied. Okay, let me use the E part. Yeah, this one. Okay, this property is satisfied. Next is this one, commutative. So if I have two vectors, three vectors, AB, CD, and EF. So if I write AB plus CD and I do the dot product of these two, this sum with sum EF. Okay, this should be equal to this. So if I add firstly these two, so I will get A plus C and B plus D, right? And then if I do the dot product with E and F, so what will I get here? A plus C times E, and below it F plus D times F. Okay, this one I will get, this vector. You can do multiply inside as well. Okay, then you will get answer. So if you check this U dot V and V dot U, so or you can do the multiplication here directly. So it will be AE plus CE, right? And BF plus DF. Okay, you can rewrite this part as AE BF plus CD and EF as two separate vectors. If you look, these two vectors are nothing but U dot V and V dot W. So it is also satisfied, this property. Next is this commutative. If you multiply AB with CD, so it will give you AC and BD, right? And if you multiply CD with AB, so it will also give you CA and DB it will give. But you know that this multiplication is commutative for real numbers. So it will be AC and it will be BD. Same. Okay, so this property is all satisfied. Now this one, if you multiply C times your if you firstly multiply a vector, then do the dot product. Let me use this. If you do C times of, not C times, let's say K times of A comma B, and then do the dot product with CD. Okay, so K times you multiplied it, it will be KA, KB, and when you did the dot product, so you will get KAC and KBD. Okay, now do the firstly the dot product. Okay, so firstly you did the dot product, so you will get AC and BD, and now multiply with K, so you will get KAC and KBD. So yeah, this property is also satisfied. So all the four properties are satisfied. So now it is an inner product. Okay, so dot product is an example of inner product. It is correct. Okay. So that's okay. Yeah. Next is norm of a vector. So norm also have to satisfy some properties like this. This is your first property, that if you have two vectors x and y and you want to find their norm, same as like length. Okay, it is. So it should be always lesser than or equal to finding the individual length or individual norms. Okay, and then doing the addition. This property should be satisfied. Okay, next property is this multiplication property, that multiplying firstly then finding the norm should be equal to finding the norm and then multiplying. Okay, this property. And third property is this. Three properties are there. Four properties for your inner product space, and three properties for your norm. That norm of any vector, if you are finding it, should always be greater than 0, except the case when x is 0. It should be equal to 0 only when x is 0. So this is something. So length that we used is an example of norm. You can check that if you find out the length of any two vectors, suppose A, B, C, and D you are having, you add these two vectors firstly. So you will get A plus C and B plus D. And if you do the norm of this, you find out the the length of this. So it will be A plus C square plus B plus D square square root. I did the dot product with itself and use the square root. Okay. So, okay, that's fine. Now find out the individual square of this, sorry, individual magnitude of these 2 points, A and B, A, B and C, D, sorry, vector, these two vectors. So if I find out, so first vector will have the magnitude of A square plus B square, square root. Other vector will have the this C square plus D square. Okay. So you can verify this thing by another, if there was a formula for this. Okay, or you can directly write. You can rewrite this part as this. That's square root of A square plus C square, right? Plus 2AC. Next is plus B square plus D square, right? Minus, sorry, plus 2B and D. So you can see that this part is matching with this. This is matching with this. C square is matching with this. Okay, and D square is matching with this.
So,
Okay,
but
these
the
four parts.
roots are different now in RHS.
Okay, the roots are different, but what I am conveying here, understand that part. Firstly, uh, you find out the square root of this part and you find out the square root of this part. Okay. Here we are adding these positive values firstly and then finding the square root. And we are also adding 2AC and 2BD. So this value can be positive or negative. Okay. Let me do one more thing. There should be an inequality expression, I think. Cauchy squares inequality, this one. Okay, it states this property. Okay, according to the Cauchy squares inequality, you can tell directly that this one plus this one should always be lesser than this one. According to the Cauchy squares inequality, it automatically states this part for dot product. I will explain it in my next lecture. Okay, that what is this Cauchy squares inequality. Okay. Next property is the C times. Let's verify these properties. Okay, I will explain it in my next lecture, whenever it will be. Just remind me once about that part. So C times of AB, if you find out let's write K times. So it will be KA, KB. If you find out this length of this, so it will be KA square plus KB square square root. So it will be K square, A square plus B square square root, right? If you write it again, so it will be K times A square plus B square. Okay. So this is this. And if you do the, if you find out the length firstly, so if you find out the length, so it will be nothing but A square plus B square. And then you multiply it by C or the constant K. So it is matching with this, you can see, right? So this property is also satisfied. Now this one, you find out that whether it is greater than 0 or not. So you know that if you do the dot product with itself, so it will be equal to this. Or if you find out the length of any vector, so it will be this. So you can see that A and B are both positive quantity, always be less greater than 0 unless A and B are both are equal to 0. So yeah, this is satisfied. Okay. You don't have to check this part. If you have already checked this inner product space case, in inner product space, if you have already checked this property, this one. Okay, so you don't have to check it again. It is okay. Okay. It is norm induced by inner product. It is same thing that firstly do the dot product that we did. So here we have to do the inner product. We are not going to use the dot product here. We will use the manually defined inner product here and then do the square root to get the norm. So here some cases are given like this and so on. Okay. So some questions, let me see that how much is remaining. Okay, that's all. So let's solve some questions here. You are given a function, here it is, that is defined for inner product space. Okay, we are going to check whether this is inner product or not. So you are given that two vectors inner product is defined like this. Okay, so let's see that whether it is following all the properties of inner product or not. So first property is that if you do the dot product with itself, means VW, and if you do it with, sorry, V with V, FVV, if we are doing, and it should be greater than or equal to 0 always. So if you do it, so you will get 2 times V square plus 5 times V square, V1 square and V2 square, sorry, because it is a two-dimensional vector. V is nothing but two-dimensional vector, V1, V2. Okay, two components are there. So this one. So you can see this is a positive quantity and this will always be positive except the case when both are 0. Then only you will get the value 0 here. So this satisfies. Next is commutative property. Okay. Commutative property, you can check V dot W. So if you find out V dot W, it will be this. And if you find out W dot V, so what would that be? So you will write 2 times W1 V1 plus 5 times W2 V2. W2 V2. So you can see it is exactly the same thing, nothing else. So commutative property is satisfied. Next property was uh, multiplicative, scalar multiplicative property. Suppose if you say that I want to find out inner product of C times of V with W. So C times of V you are doing. So you can write here C times of V1. So you will get 2 of 2C times V1 W1, right? And 5C times V2 W2. So you can see if you did the dot product firstly, you can remove the C part. Okay, what you can write it as C times 2V1 W1 or then plus it is, sorry, it is plus 5 times V2 W2. So it is nothing but if you do this, so it is equal to C times F of VW. So the fourth property is also satisfied. The distributive property is remaining. You can check for that. It will also be satisfied. Okay, so it is satisfying the inner product symmetric condition. That was this. It was bilinear positivity condition that it will always be positive. Sorry, this one. Symmetric condition, I think. Symmetric condition, what was that?
Sir,
Yeah. Yeah. The symmetric condition means if we do VW, then it should be equal to WV. Yeah.
sir, in this one you have mentioned, right, f of CV comma W, this one.
Yeah. This one.
So in this one, sir, since you have taken the property of the transformation, right, basically.
Yeah.
So like in this one, sir, shouldn't
We
it be
did
CV comma CW?
what?
Sir, in this one,
Yeah.
FCV, shouldn't it be CV comma CW inside?
CV comma CW. No, it should not be. What I am saying that we can multiply any one vector, scalar multiplication we are doing. We are not it is not a group. Okay. This is a function means here it is written as V dot W. We are doing the inner product between these two vectors. So firstly, if I multiply this, okay,
Mhm.
then it should be equal to V times CW and it should also equal to uh, C times V dot W.
Okay.
Whether I do this first, whether I do this first, or whether I do this first means it should satisfy all these three conditions. Doesn't matter whichever thing I am doing first, whether I am multiplying the vectors firstly or I am multiplying the scalar firstly. That is the property. Okay. Positivity is satisfied, symmetric satisfied, bilinearity, I think it is saying distributive property, I think. Not exactly sure. I'll check that. F is an inner product space. Yeah, F is inner product. When all the four conditions are satisfied, so we can conclude. Okay, same here. You can check for this part as well. all four properties, you will calculate this. Okay. Next is this. Two vectors are given, A and B in R3, and the two vectors satisfy the triangular inequality. Okay. Means if you add any two vectors, then it will always be lesser than this one. Okay. So if you add these two vectors firstly, so if you add suppose 2.4 you got, and 3 sorry 4.3 you got, and then minus 5, okay, it is minus 3.2 you got. Okay, this is your vector. So it is saying that finding the magnitude of this. So if you find out the magnitude of this, so it will be 5.76, right? 43 will be 25 minus 7. It will be 18 and 49. 118.49 it will be, and 32's power this one, it will be plus
1024.
1024, so 10.24. So if you add all this part, you will get roughly, it will be zero point 0.5 and it will be 0.25. So sorry, if you add these two parts, so it will be 1 and zero point 0.5 you can write 1 here, 19, 24, 34,
So you're
right?
finding the norm. So
Yeah, the norm. But I think I should use, okay, I am using the dot product here. Okay, maybe it could ask you for the norm using any product space. Okay, any inner product space it can use. Okay, I am here using the dot product. It is not given, so I use this. Okay, so 34.5 I got. Okay, now let's do individual finding the magnitude of this. So zero point 0.4 square, it will be 0.16. 1.3 will be 1.69, right? And 2.2 will be 4.84, right? So if you add this thing, so let's do this as well. So it will be 4, 9, and 25, right? So if you add this, so you will get
yeah,
34 plus 4,
yeah.
38. So you can see the 38's root will be greater than its root, right? Doesn't matter whatever the value of this. You can leave this part. So it is already, because it is positive, so it will also increase this value, not going to lower down. So it is satisfied. So it satisfies the triangular inequality. This is called triangular inequality. Next is the two vector satisfies Cauchy squares inequality. That if you do the dot product and then, sorry, yeah, if you do the inner product with or dot product with itself, sorry, between these two, this should be lesser than, yeah, like this. So what it is saying, what is this saying? It is saying that if you do the dot product between these two, so you will get 0.8. Okay, and here you will get 3.9, and if you do this, you will get 11, right? So if you add all these parts, you will get 14, 15.7, right? You will get this. So this is your, you have to do the square root of this. Okay, so let's do the square root as well, and now individually find out their magnitude or norm. So if I find out, so zero point 0.4 multiplied with zero point 0.4, it will be 0.16, it will be 1.69, it will be 4.84, and here we have already find out it was 38 square root, right? So you know that root 38 times, if I do this is greater than 1, right? So it 38 will be increased its value, so its square root will be greater than this part, right? What I am saying, that whatever be the 38 and this is some value greater than 1. Okay, so if I multiply it with 38, so this value that I will get, it will be more than 38. So its square root and square root of this 15.7, which one will be greater? This one, 38 square root. Okay, So
Sir,
yeah,
which property you used? Cauchy squads. This one.
the Cauchy squares inequality. We are checking this whether it is satisfied or not. This property is called Cauchy squares inequality. This one, that if any two vectors dot product or inner product is lesser than or equal to their individually magnitudes product, then we can say that it is following Cauchy squares inequality. Okay. Okay, three questions are remaining. So this one is given here. V is given a vector like this. It is given like this. You have to again check for the inner product things like this. Okay. So you can check by yourself. Uh, because in this one, the scalar multiplication will fail. Because if you multiply this V with C times, okay, so what you will get here, C square V1 square W1 square plus CV1 W2 square. Next will be C square V2 square and W1. Okay, so here you can see if I am multiplying V with C, then it should be equal to C times this part, right? But you can see somewhere it is multiplied C square and C. So this property doesn't hold. So that's why it is not an inner product space. Okay, you can check by yourself. If still you face some problem, then you can tell me. Okay, this property will fail here. Next is this one, ABC, A1, B1, C1 in R3. What are the possible candidates for a norm? Norm, you have to check which one is satisfying the norm. So you can see here, it will satisfy because it is nothing but you are already observed this, that it is dot product of itself. If I do A1, B1, C1's dot product with itself and then do the square root, this is actually the length that we are using. So it is basically a norm. So this is satisfying the property of norm. Okay, this one is not going to satisfy because norm of every vector should be greater than 0. So you can see this value will go below 0. If suppose I take 1 minus 2 and 5, so in this case if I use this as norm, so it will have minus 1, but length cannot be negative, so you can remove this part. Same here, if you add all these, suppose it is minus 5, it will be minus 6, right? Addition, so it will also fail. Next is max of these parts, whichever is max. Suppose all three are negative, minus 1, minus 2, and minus 3. So maximum is this, minus 1. So it is still negative. So it is false. Minimum, minimum is minus 3. It is also wrong. Here, maximum of the magnitude or the, not magnitude, it is, yeah, magnitude you can say, or it is modulus function. We are applying the mod, means taking only the absolute value, positive part. So yeah, this can be. You can verify the other properties for this. The other properties are there, like C times of V's norm should be equal to C times of norm of V. So it will be same because if you are finding A1, B1, C1's norm, so suppose A1 is the greatest. So if you are finding K times A1, K times B1, K times C1's norm, so here it will also be greater. Okay, still it will be greater value. Its magnitude will be greater. Okay, such like A's magnitude is greater, so this will also greater. So this is satisfying this property, and one more property is remaining, I think. So you can check that. Okay, not too hard, it is quite easy. Next is this one, where we have to check the correct options. So it is asking which one is inner product space. So you can check this. It will satisfy all four properties. Next is this one. It is an inner product space or not? Okay. So it should satisfy commutative property. Means if I multiply x comma y, x y I am doing, then it should be equal to y comma x, right? Symmetric property, or not commutative. Symmetric. Symmetric, not commutative. It is symmetric. Sorry. Okay. So if you do x1, x2 with y1, y2, then it is equal to, it is not less than greater than or equal to. Okay, it is defined like this. We define the dot product like, no, sorry, inner product like this. Okay, so x1 x2 you are doing with y1 y2. So you will get x1 magnitude plus 2 y2s. Okay, so if you do vice versa, y1 sorry, yeah, y1 y2 firstly and x1 x2 later, then you will get y1 here and plus 2 times of x2. So you can see both are not matching, so that's why it is not inner product, right? Next, continue here. It is an inner product. You can verify the 4 properties for this, and here you have to check whether it is an inner product or not. So x1 y1, this is okay, minus x2 y2, it is okay. Then if you do the dot product with itself, sorry, inner product if you are doing with itself, so let's find out. Suppose you have x1 y1 and you want to do with x1 y1 itself. So what you will have here, 3 times x square minus 5 times y square, x1 square and y1 square, right? So you can see that its self product should be greater than or equal to 0. But here it is going, it can go, uh, it can be less than 0. How can it be less than 0? You can put the value of y something greater than x. Okay. Suppose I put one value of this 1 comma 7 this. So this will be 3 minus 5 times 49. 3 times 1. Okay, so you can see it is negative value. If it is negative, then it is not following the property of positivity, so that's why it fails for the inner product. So that's done. I think up to this part your week 7 is. So any other query if you are having now, then you can ask. No other queries?
No, sir.
Anyone having any query related to anything, any concepts of week 7? Any practice assignment activity related? You can tell. Nope.
No, sir.
So we'll be having revision for maths also, right? For quiz
Yeah,
2.
on maths revision session, actually, instructor takes some sessions and let me stop this recording. And on the day before quiz and 1 day before that, I took the session. Okay, I am going to take. I last time I took, and I will take for the quiz 2 as well.
So for quiz 2, like which of the topics like are most important, like which carry maximum weightage?
For quiz, it is not specific that which one is going to carry maximum weightage and like these things.